Recording in progress.
Good evening, everyone. Welcome back to last live session for the mp4 course, Advanced Transition Metal Organometallic Chemistry. So today we are going to discuss about the week 12 lectures as well as their assignment problems. So this would be the last live session for this course, and then we'll be having an exam for it. So let's start with the lecture 56, which is about the organometallic catalysis reactions. Namely hydrogenation of alkenes. So just in case those who have missed whatever we have done in the last time. So generally we were talking about the carbonylation of alcohols and some olefination reactions and all those things, oxidation of your olefins, and mainly we had seen oxidation part in the last lectures, but here we will be talking about the hydrogenation or reduction of the alkenes. So let's get started. So as the title suggests, says that hydrogenation of alkenes, it's a complementary reaction to the oxidation of alcohols, because last we have studied the oxidation thing, and here we are talking about the hydrogenation. So hydrogenation is complementary, it's just the opposite of what we have seen in the oxidation. So for example, oxidation is also called as loss of electrons, and if hydrogenation, and the other term would be the reduction using a reducing agent. Here we are using a H2 because we have to do the hydrogenation. So it's a gain of electrons. Or in hydrogenation, it's a gain of hydrogen over there, right? Hydrogen gets attached to the molecule. So only those who are unsaturated, they can only undergo the further reduction. Otherwise, there is no saturation or valency left to get or connected to another hydrogen molecule. So the dihydrogen, the dihydrogen activation in the homogeneous solution can be achieved as. So here we are doing the hydrogenation. For hydrogenation, we can actually use a lot of hydrogen giving agents, but here we are mainly focusing on the H2, which is a sustainable source. So this dihydrogen first has to get activated to get connected to your substrate to, and for that matter, we are talking about the alkene. So if I'm taking this alkene, this ethylene, so this is having an unsaturation, and it can accommodate two hydrogens at one hydrogen molecule at one time, and can give you the alkane over there. So ethane can form. So for that matter, if we are using H2, first of all, this HH bond has to be cleaved. It has to get activated. That's why we call it as a dihydrogen activation. And dihydrogen activation can happen in three ways. Firstly, homolytic cleavage. With the homolytic, you can understand that it will cleave in like a homolytic fashion. Both the components would be having the hydrogen in a similar manner. So both of them, they are having the same, this bond will be going like this particular way, and it would be having like equal contribution of the electrons. So if we have a cobalt cyanide, a Cn, and if it is H2, then it will give you the COCN5 and H. This is called a homolytic cleavage because both molecules will take one H. if we are taking the heterolytic cleavage, so one will take as an H and H negative, and other will go as an H positive. That means the charge is not, the charge has been now distributed and they are going as a, for example, here. So we mainly are talking about the dihydrogen activation. And this can occur in three possible ways. Firstly, the homolytic one. Heterolytic. And the last one is oxidative addition. So here we are talking about if we have H and H. So both will be having equal electrons and they will contribute the same way. Whereas in heterolytic, one will take up the electrons and other will become positive, and the first one become, there would be a cation and ion thing. That would be a radical thing. H dot and H dot. And in oxidative addition, you have already seen if we are going with this palladium 0, for example, and if I am having this HH, so it gets bind with H, and both will take up the electrons from the palladium, and palladium now becomes a 2 positive in nature. So this is where the dihydrogen activation can happen, and this is what the examples have been given. For example, here the cobalt, both complexes which are having the cobalt as a metal center, they are taking the hydrogen as a one radical over there. The second one in H2, the heterolytic, the platinum is taking one hydrogen as a H negative and releasing that SnCl3 also with the loss of H positive. And in the last, where we are using a Wilkinson catalyst, rhodium, that H2 is coming and both the hydrogens are connected with the rhodium. That is called a oxidative addition. Okay. So this is the way, the first step, because we are talking with hydrogenations, we need to know how the hydrogen molecules get activated. Now, for the hydrogenation of alkenes, the first catalyst that we know that is called as Wilkinson catalyst with the formula of PPH3, rhodium and chloride, where rhodium is in +1 oxidation state with a coordination number of 4. The first practical application of homogeneous hydrogenation catalyst is this one, where the rhodium catalyst has been used. So Wilkinson catalyst involves oxidative addition method of dihydrogenation activation. Hydrogenation of alkenes and alkynes, they happens generally at the room temperature like 25 degrees and at standard pressures like 1 atmosphere. The hydrogenation of terminal double bond is faster than the internal ones. This is very important to know, that if you have been given a terminal alkene and if you have been given a, so for example, an internal alkene, so this would be having faster rate compared to the other one. Functional group tolerance it is having. So if we are having a nitro, if we are having a CHO, so there is a chance of reducing these species also. But when we are using this particular catalyst, it makes sure that other functional groups, they do not get hydrogenated in presence of the alkenes. So the priority and the selectivity is very high. The dihydrogen addition happens only in the cis fashion. So these are very important points that has to be kept in mind while solving the questions and understanding the mechanism. So here is a mechanism for, I will just do like this for you. So as we are saying here, okay, so this is our catalyst, this is our Wilkinson catalyst, where P stands for your phosphorus group. So the way is like it is connected to these lone pairs of phosphines, which is further connected to pH, pH, pH. And here is the chloride. And because of this chloride, it is becoming +1. So firstly, the loss of one phosphine molecule, and it will be having two phosphine and one fluoride. Still, it is in +1 oxidation state because phosphines, they do not carry any charge to the complex. Now, the first step is the oxidative addition, as we were talking about, how many ways are there where we can activate our hydrogen. So the first way is oxidative addition of the H2. So the H and H has been coordinated with the rhodium, and now rhodium is in +3 oxidation state. Here it was in +1. Now the second step comes as alkene coordination. So here we have an alkene, which is a terminal alkene, and it is coordinating with your rhodium as a pi interaction, it is there. And third step is the insertion of your alkene. Or we can say that hydrogen bond is also going. So this hydrogen bond, which is near to this one, it will go and attack over here, and then CH2 will attack on your rhodium, and therefore this process will happen, and now it has lost its unsaturation. Now, once this is there, now cis trans rearrangement happens. Right now it's in trans, now it becomes cis. So this molecule and this molecules, they undergo the reductive elimination, and we end up having our product. So this is our desired product, which is an alkane. So I hope you have understood this. So as we started with the rhodium complex, which is the Wilkinson catalyst, with the loss of one phosphine, or if we are giving phosphine to this one, it will again give you this Wilkinson catalyst. So it is an equilibrium. When the first step is the oxidative addition of your H2, because it has to get activated so that it can bind with your rhodium system. Then the rhodium goes from +1 to +3 oxidation state. That is why it is called as oxidative addition. Followed by the alkene coordination. Whatever the alkene that has to get hydrogenated, it will coordinate with your rhodium as a pi interaction. Now, since it is having a hydride in a very close proximity, it will go and bind with this carbon, and then CH2 negative will attack on your rhodium. This is called the insertion. Followed by when these alkane moiety and this H are in cis and trans position, for the reductive elimination, it will always occur as a cis elimination. So the cis product will go out as a reductive elimination product, RCH2CH3, and ultimately we'll be making this active catalytic species again. So this is our active catalytic species, which is meant to make number of catalytic cycles. So these are certain steps. That step one is the oxidative addition of your H2. This is done. Then coordination of your alkene. Alkene insertion that we have just seen that once that alkene is being formed, if we have this rhodium and it is occurring as RCCH2 and it is having hydrogen. Now the next step was to have RCH2, CH2 and rhodium. So this is attacking on here and this is attacking here. So this step is the rate determining step where it has to, from the coordination, it has to get to inserted it with the rhodium. So this step is very, very important because it's the slowest step. So the slowest step among all the catalytic steps is called the rate determining step. So the trans-cis isomerization that we have seen, and ultimately it's a reductive elimination to have the product back. Now we have the terminal alkenes if we are taking, for example. So again, so this is another different kind of that catalyst. Earlier we were having RHPPH3 and chloride. Here we are having RHPPH3, H and carbonyl. So it is already in 5 coordination, and it is involving a carbonyl, and it is having the hydrogen already attached with it. So with the loss of phosphine, because it can go easily in comparison to carbonyl group, it is weak compared to the carbonyl. So both are 2 electrons. So phosphine will go out. Now it has become this catalytically active species. The first step here, now it becomes as a alkene insertion or coordination firstly. So the first step is the coordination of your alkene. And as you can see over here, now this hydrogen will go and attack over here. This is called the alkene insertion, which is of course a rate determining step. Therefore, it has become a CH2CH2R. Now we have a carbonyl and we have a CH2CH2R over there. But right now, we should not forget that we have an H2 also, which is going to hydrogenate. So the H2 oxidative addition now happens because it was still in +1 state. It now has become 3 in nature. So both H and CH2CH2R, whichever are in cis positions, they go and form the alkane product, and we generate the catalytic active species again. So this is the mechanism for this particular complex. So here in this lecture, what we have seen, we will just take a summary of it. So firstly, we saw that hydrogenation is it's complementary to oxidation. So these both processes are complementary to each other. Second, we saw that for hydrogen or dihydrogen activation, we have 3 processes. One is homolytic, where H and H just will go like a radical form. Heterolytic, where one will act as positive, other as negative. And the third method, which is generally used in the catalytic CC coupling or any other reactions, that is oxidative addition. And third, what we saw is using this PPH3 whole thrice rhodium chloride, which is a Wilkinson catalyst. We saw the mechanism and how it is working. And also we saw the mechanism with PPH3, P, rhodium, HCO. Also, besides this, there were some features. For example, the features in Wilkinson catalyst. Firstly, that alkene insertion is your rate determining step. That means it is the slowest step. That's why we can determine the rate of the reaction, slowest step. And this hydrogenation will always occur in cis form. Third was that terminal alkenes have more rate of reaction for the hydrogenation compared to the internal alkenes because of the steric effect. So these are the following features of it. Now we will move to the lecture 57, which is about, earlier we saw and we read about the hydrogenation of alkenes. Now we are specifying that it has to involve the asymmetry, that means chirality. So here, I will just zoom it out for you. Okay. So here we are using a system which is having a molecule which is ready to leave, and solvent molecule can come and attach over here. So for example, if I am taking a rhodium catalyst system where the phosphine is being connected, for involving a chirality, the phosphine has to, the bidentate ligand has to be chiral in nature to make the whole complex as a chiral molecule. Firstly, we are giving a hydrogen source, and since we have an unsaturation here itself, it will get saturated and it will leave out as a C8H16. So this molecule first gets hydrogen. The H and H will go over here, all the 4 carbons, and it will leave as C8H16. Once it leaves rhodium in positive, so it is having 2 vacant positions, and since we were using a solvent molecule, could be THF or CH3CN, which have a coordinating capacity, they will get bind with your rhodium. So that ultimately at the moment of point, they can leave also and rejoin again. The first step here becomes an alkene coordination, as we have seen in other reactions also. As you can see, this is a pi interaction right now. So the other step is the hydrogen activation, or we can say hydrogen oxidative addition. So here rhodium was in +3, now it becomes in +1, and now it becomes in +3 state. So H and H are there. Now if you will see, both are symmetrical CH2 CH2, so any of them can go to CH3 form. So this has become CH2 CH3. So here the rhodium as a plus sign is symbolizing the chiral thing. This is a chiral molecule. That's why everywhere it is written like this way. Now you can see both H and CH2 are cis to each other. So there is no requirement for the cis trans rearrangement. Ultimately, reductive elimination happens and it will cleave as an alkane. Okay. So now the asymmetric hydrogenation of alkenes, the catalyst L2 rhodium Sol2, where L we have seen, along with the chiral diphosphane ligands hydrogenate the prochiral alkenes to give the chiral products in high in initial selectivity. So what the possibilities that we can use for so making this particular system as chiral, the whole catalyst, we need to involve the chiral diphosphane ligands as shown over here. So these 2 centers are chiral. So when phosphine will coordinate with the rhodium, the chirality will get employed. Similarly, this is another chirophos, and this is norphos, where it is having 2 here chiral centers and 2 here chiral centers. So these are some examples. The chiral center of the diphosphine ligand can reside in the carbon framework or the phosphorus framework. So here, as you can see, it can come on the carbon framework or it can go to phosphorus, which can bring to the chirality. The chiral induction step is the oxidative addition of the H2 to the diastereomeric eta2 olefin complex. So here, for the asymmetric hydrogenation, what kind of systems that we use? This system is a binap system. And this is coordinating with your ruthenium, which is bringing, as you can see, this is wedge shape and it is coordinating with the ruthenium and chirality is being bringing. The van der Waals repulsion of the PPH2 unit governs the chirality of ruthenium coordination sphere. And for the reaction of the catalyst substrate complex transfer the chirality to the product. So how the chirality is being there, because of the van der Waals repulsion, it will transfer the chirality to this whole thing, and then when it reacts with your substrate, it will transfer the chirality to the product also. And the naphthalene, so these 2 are the naphthalene rings, and they are having a bond angle of 66 degrees. So this Noyori catalyst in asymmetric hydrogenation, how we can use it? So here binap is already a chiral system, and X could be anything. So we can asymmetrically hydrogenate the functionalized ketones where Wilkinson catalyst fails. So if we have this binap ruthenium CX2, where this is a chiral, and we have PPH3 rhodium Cl. So if it has to asymmetrically hydrogenate the ketone, it will not do, but it will do. So this is the advantage. For example, if we have this ketone, and now since this is carbonyl group, so it has to get hydrogenate to become an alcohol. Firstly, we have used an S binap. So this is one enantiomer using these conditions. So it will give you OH with a dash form. If you are using the R binap, so it will give you the OH with the, so this is another enantiomer over here. So this is the advantage of Noyori catalyst over the Wilkinson catalyst. This is very important. So what we have seen in lecture 57, so we talked about the asymmetric hydrogenation of alkene, and the take-home message was for chirality, the chiral phosphine, diphosphanes have to be involved, have to be used. And we found that BINAB, sodium X2. So this is called as Noyori catalyst. And this is having an advantage over Wilkinson catalyst, which is nothing but sodium pH3 chloride for asymmetric hydrogenation of functionalized ketones to alcohols. So this was the summary for lecture 57. Now we will move to lecture 58, which is still the continuation of asymmetric hydrogenation. So the Noyori catalyst in asymmetric hydrogenation, the asymmetric induction is due to the chelation of your carbonyl group and the heteroatom of the substrate to the BINAB. So suitable substrates like 1,3-diketones, beta ketoesters, and aminoketones, etc., can be used. For example, if we have this system where carbon, the ketone is there, and we have an OH, which is already a chiral also. So when we are treating it with so we are starting with this particular carbonyl, dicarbonyl system, and we are using a BINAB system, which is a Noyori catalyst. And firstly, because of this R form will generate it. The OH will get a chirality over this center becomes a chiral. And since if we are using H2 in excess, the other carbonyl could also get reduced or hydrogenated towards the OH, and this becomes 100% enantiomer selective. With the mesoform also, like any other thing, we can have a plane of symmetry over there that becomes a mesoform. So this is how the Noyori catalyst has been used here. It is also successfully employed in various organic and natural product synthesis. For example, we have to have a beta hydroxycarboxylic ester. So we have started with the substrate. So this is our substrate where we are having two carbonyl centers. And when we are using H2 at 80 to 100 bars, so this system becomes a chiral, and enantiomer selective yield is 98%. Here, the halogen atoms in the substrate also suitably anchor the catalyst so as to give the enantiomer selectivity. So if we are having bromine at the meta position or the para position, so this kind of selectivity won't be able to see. But on the ortho positions, because of this anchoring happens, so this becomes undergoes the hydrogenation, not the meta and para. So they don't go in any kind of this hydrogenation. So here we can see we have a carbonyl over here. One will become the H, another, this is having a wedge bond, and the H would be like this. So here it is having a 92% enantiomeric access. Now to form another kind of molecule, so the synthesis of anti-inflammatory S naproxen. So how the application is coming, so this is basically the application of your Noyori catalyst, where the asymmetry is bringing a lot of synthesis of the lot of molecules. And if we have a center over here, which is a terminal alkene, and you're using a hydrogen, it will get activated in presence of your Noyori catalyst. You need to be sure that it is using an S form. It could be having an R form, and then the conformations would be different. So this is the one. Now, the PINAP Noyori catalyst, which is having the ruthenium one, it is superior to the rhodium ones in the asymmetric hydrogenation. Yes, I have. So, sorry for this mistake. It is ruthenium. So that is what the advantage is over here. So the Noyori catalyst is having ruthenium-based system, which is superior than the rhodium ones in asymmetric hydrogenation. So firstly, the hydrogenation of alkenes has been started with the rhodium-based catalyst system, where we saw the two catalysts. One was this Wilkinson, PPH3 chloride, and other was PPH3 rhodium HCO. So both were able to do the hydrogenation of it. But now if we are talking about this Noyori, they are only prone to give you the asymmetric hydrogenation, and the rhodium ones fail in that. So for example, if we have the alkenes with the CO group, so how it is going to work? So first thing is that we have this particular moiety, which is a Noyori catalyst, where SNS is a solvent molecule. We are using a serial bond C over here, and it will give you these kind of coordination. The alkene, firstly, the alkenes are getting coordinated, and also because of the lone pair on the C-dol bond, we can also coordinate with your rhodium. Firstly, the H2 step, that oxidative addition would be very fast. As you can see, H and H are coordinating with rhodium, and ultimately the H will be transferred to this bond, and you will be ending up having this S form. Similarly, if we are going in this direction, where here the H2 becomes a bit slow, and ultimately we will be having an R form with a 5% only. So the carbonyl group is actually assisting in giving us stereoselectivity by anchoring with the catalyst system. So here it is anchoring here, so H and H can transfer, but having an addition of this hydrogen over here becomes very difficult because of the anchoring position, and therefore the R form becomes a lesser number. Now we have the C-dol bond C, NHAC, and another example where we are having this, we are making this L-DOPA for the Parkinson disease. This is another example or application. Now for the lecture 59, organometallic catalysis reactions, this is different from the hydrogenation what we have seen. So hydroformylation, that means the formation of CHO group or any other that R group. The hydroformylation, or we call it as an oxo process. It is the largest scale industrial application of homogeneous catalysis. So the preparation of this propanoldehyde from ethylene and synthesis gas. Synthesis gas is nothing but your carbon monoxide and H2, which we have read earlier. In presence of heterogeneous cobalt catalyst was patented by Rowland in 1938. The actual catalyst is HCC carbonyl thing, which is formed by the reductive carbonylation of cobalt oxide with H2 and carbon monoxide. So what is the reaction for this hydroformylation thing? The addition of H and HCO across a double bond that happens. So we are taking an internal or terminal alkene. This is nothing but your terminal alkene, that ethylene. We are using synthesis gas. So this 2 makes a synthesis gas, and this is our catalyst. These are the reaction conditions. And ultimately, as you can see, we started with carbon 2 and we ended up having carbon 3 with the aldehyde group over there. So this is what is called as hydroformylation reaction. Now, if you will see that relative activity of the alkenes, if we are starting with the terminal alkenes, they would be having more rate compared to the internal one, as we have discussed. And also among those terminal ones or the internal ones, the steric effect, less the steric effect, more will be the reactivity. So this is in terminal, this is in internal. but they don't have any substitution, so terminal is more than internal. Now it is having a substitution insert terminal, but it is having a substitution insert internal, so it becomes more. Here we can see the substitution is even more higher. That is why it has come with the least reactivity, right? So the hydroformylation, the C315 aldehydes are also produced. So we are not restricting ourselves for particular one CHO group only. It continues to give you almost C15 aldehydes also from the respective olefins by the oxo process, which can further be converted, because once the HO group is there, we can reduce it to amines and carboxylic acid. We can oxidize it to carboxylic acid or further reduce it to alcohols. So this is the way. Firstly, we are starting with this alkene, and then we are getting CH over here. If it is undergoing a condensation reaction in presence of base OH negative, it will give you this product. Ultimately, on having this water loss, it will form this alkene, and using or treating with the hydrogen, it will again and continue to give you this alcohol system. Also, if both will combine, and they can give you the OH, and this is also like, this will get reduced and will give you corresponding alcohol over there. And if it is getting reduced, it will give you corresponding this alcohol. The hydroformylation of the terminal alkenes is industrially very important. The first step is that we are having this 3-carbon chain, and this will get form a CHO over here. So firstly, it will form the CHO. So first step is OH is not going to do anything. So there, C don't want ONH, so this will become CH2. So this CHO is there, and 1, 2, 3, and 4 carbons, 1, 2, 3, and 4 carbons. And ultimately, when the hydrogenation is happening in presence of the Ren nickel, it will further go to CH2OH. So this is what we are forming here. So the conjugated dienes has a problem of isomerization during the. So this is a disadvantage, that if we have dienes in the conjugation, then how to have the hydroformylation to that. That is the disadvantage. So this is the mechanism for hydroformylation reaction. So what we are starting here with. Okay. So the first step is we started with this complex. This is actually being formed from the cobalt oxide and other things, but it is making a complex over there, which is HCCO44. So the first step is to have this catalytically active species with the loss of one carbonyl group. And the second step is the alkene coordination, as you can see. Here it is coordinating with your cobalt system. Then because of this, our H group is there, so it will transfer to this hydride. The hydride transfer will happen. That means alkene insertion is happening. After the alkene coordination, the next step is the alkene insertion. Now carbonyl insertion is happening. Coordination, we can say. The lost molecule will come into picture. Again, it becomes CO4, and then CO can insert into the alkane system. MH, MR bond, that is metal and that is alkane, and CO can insert between that. So CO insertion will happen. You need to follow this trend, that alkene coordination followed by alkene insertion, then carbonyl coordination and carbonyl insertion. Ultimately, oxidative addition of the H2, your reducing agent or the hydrogenating agent. Then ultimately, we will be ending up making this H, and that H, which is coordinated with the cobalt and this particular group, it will undergo as a aldehyde product because of the reductive elimination. So 7 steps are there. So the rate determining step here is the oxidative addition of the H2. In other hydrogenation of the alkenes, you saw that alkene coordination or alkene insertion is the rate determining step. So here the step 6, which is having the H2 oxidative addition, that is your rate determining step. That means the slowest step. The hydroformation formylation results in mixture of the aldehyde, so it can give you the linear formaldehyde or branched one. The alkene insertion step 3 is the cause of the mixtures, because if you can see over here, we are inserting the alkene here, so that H can go either here or it can form the CH3 over here. So here, if you need to have that linear or branch form, so what is the culprit? That is the alkene part, that's step 3. Now we have a phosphine modified system over there. So the phosphate modified cobalt catalyst and rhodium catalyst that give the linear products. So if we are particularly using these systems, then they will give you the linear products and no branched one over there. And the reaction conditions are relatively milder if we are using a rhodium catalyst. Here we are using the cobalt. Now we will see the rhodium catalyzed hydroformylation. As we have already talked about, the Wilkinson has developed that rhodium catalyzed hydroformylation. So the Wilkinson catalyst that we have just saw is nothing but the PPH3, which is coordinating with your rhodium and a chloride. And this is what we started with. Now this Wilkinson catalyst avoids the drawbacks of the cobalt catalysis and is very important method for the production of the propene. For example, if we have this alkene, which is a terminal alkene, and we are having a carbon monoxide with H2, which is called as a synthesis gas, and using a rhodium catalyst, keeping these conditions, we are ultimately generating a aldehyde with the, if you can count the number of carbons, 1, 2, 3, and 4. One carbon should be less over here. It should make only CH3, CH2, and CHO, because only one carbon group is involved over here. So rhodium, earlier we saw the cobalt catalyzed hydroformylation. Now we are looking at rhodium catalyzed hydroformylation. The complex has been changed. So the first thing that we are using, this complex we have already seen the lecture 56, where carbon monoxide is already connected with the rhodium. So with the loss of PPH3, one molecule can go out, and among carbon monoxide and PPH3, both are 2 electron donors, but this will form strong bond with your metal, so it will not leave out, whereas PPH3 is a weak ligand compared to the carbon monoxide. Carbon monoxide is a very strong pi acid ligand. So PPH3 will go out, and if you can see, this is an equilibrium sign. If I'm giving PPH3 back to this particular complex, it will go back to this original form. So this is the catalytically active species. So generally what happens, even if you are starting with a catalyst system, it doesn't mean that it will stay in that particular form in the whole mechanism. For whatever the species which is continuing the whole cycle, that is called as a catalytically active species. So as you can see, the cycle is starting from here and the circle ends over here only. So this is why we are main focused towards the catalytically active species. One second. Okay. So now,
जो एल्कीन है वो रोडियम के साथ कैसे जुड़ता है, जो मतलब जो पाई बॉन्ड है वो रोडियम के साथ कैसे इंटरेक्ट करता है, वो तो दूसरे बारे में भी इंटरेक्ट करता है, ठीक है.
Here we are talking about the pi interaction only. So जब pi electrons are there, so they can interact with your rhodium very easily because there are empty orbitals on your rhodium, right? Firstly, it will interact. It is not a bond over here. Don't take it. So this way only show as a dash bond and it is interacting. Okay, there is a coordination between your bond, pi bond, and with your rhodium. So it is not like directly coordinating. Or we can say that both the carbons, so here it is in eta2 form. Both the carbons are having equal electron density on your rhodium. That's why it is shown as a pi interaction. But if you will see in the next step, now it is forming a proper bond as a like sigma bond that we see. So this becomes an alkene over here. Okay.
So firstly, lone pair interaction मतलब जो CH2 pair
pi electrons, firstly they get interacted with your rhodium. They can easily interact because they are not going to localized on something. Once that happens, as you can see, if I'll make it as a dash bond, firstly this is a pi interaction, and since this H is very close to the CHR and it will get hydrogenated and this will transfer over here, what happens if I have this RH and it is coordinating? This is only making a direction, like where it is going to attach. So the firstly H, which is H negative, it will attack on this carbon, and this pi goes here. It becomes CH2 negative. When this is CH2 negative, this will attack on your rhodium back. That is why now it is making CH2 CH2R bond. So this RH bond gets cleaved, and the new bond what has been formed, that is between CH2 and rhodium. That is why it is now CH2 CH2R. This is a sigma interaction, which is way
अच्छा
stronger compared to the pi.
मतलब कार्बोन इसके बारे में दूसरे बारे में कार्बोनिल जब ब्रिजिंग लिगैंड जैसा काम करता है तब वो तो लोन पेयर डोनेट नहीं कर सकता तो वो कैसे इंटरेक्ट करता है मेटल सेंटर के साथ
Actually, उसमें there are some electrons which मतलब when we talk about the metal, there are the orbitals we are actually talking about. So that is why when two metal centers are there, then it will give you one electron here and one electron here. So that two electrons for a one particular metal that has been gone into like two metal centers. So it is not a like particular interaction, like it is not making a one full bond with both of the metal system. That is why in bridging case, the interaction between the metal and carbonyl becomes reduced, or the bond becomes weaker compared to when it is forming with the metal C, the triple bond group. Here, because the two electrons are coming, one lone pair is there for sure on the carbon. That is there. That is why it is interacting, because it is not coming up with the charge. But once we are having this kind of system, the two electrons which are having, which are localized on the carbon, they got distributed between the two metals. That also, when it bridges with the metal three metals over there. So that is also possible. So when we have a mu2 bridging or something like that, there the coordination or the bond strength becomes. So here, because it is not a like pure bond, it is not making any pure bond, it is not coming with the charge. If we would be like looking at this particular system, when we talk about the carbon, we say that it is not having any charge, it's zero. That is why the metal is zero. So then it can go for the bridging systems also. That is not a problem. But those systems which are involving a one full sigma bond or that kind of interaction which is bringing any charge, there the bond has to be very strong. And once it goes into the bridging, then the bridging makes the interaction between that particular metal and the ligand that becomes very weak. That is why here also. Earlier we were talking about the alkene which is having a pi interaction, and that bond was weak, not very strong. But as soon as it goes and make a sigma bond over here, compared to this alkene, this sigma interaction bond would be very strong. That happens with the terminal carbonyl also and bridging carbonyl.
मतलब एक ही कार्बोनिल तीन मेटल के साथ बारी बारी में इंटरेक्ट करता है
Then we can't say that it goes like bari bari karke. It's like ki, equal distribution of the electrons with the three metal centers. That we can say, like if we having a two electrons, it will distribute it into a three metal centers. Something sometimes these systems they definitely occur. For example, if you will see what I should say, if we have a BH2, you might have heard about the diboranes B2H6, right? So it goes like this. Now we know that hydrogen can only give one electron. So how it is making two bonds with the boron? So these are not pure bonds. Generally, like Al2Cl3 or Al2H6, we call it as a banana bond because there it is like two centered, three electrons, two centered, one electron, two centered, two electrons. So these kind of coordinations or the bonds will occur. So this is also happening with your metal system. Even if two centers or three centers are there, the total electron count is 2 only. So that will be distributed among all these three centers. So they are different class of complexes. Okay. Yeah. So here also, na, like when we talk about the B2H6, so we generally say that okay, boron के साथ जो यहाँ पर side पे HH लगा हुआ है, that are giving only one electron. But what about those which are in between or bridging with the two boron atoms? There we don't say ki, okay, now hydrogen is giving 2 electrons. It is not even having the lone pair. So how it is occurring? It is like, even if there is one center which is giving the electrons, how many centers it is coordinating with, what we are calling it as. So it becomes a 3 center, 1 electron, or 2 centers, 1 electron. Like that we talk about. Okay. So we have gone beyond the topic. So I will just erase this particular thing to explain the mechanism. Okay, so what we were looking at. So here actually I'm explaining how the hydroformylation occurs. Hydroformylation is nothing but when we have an alkene system and we use a synthesis gas. Synthesis gas is a combination of carbon monoxide and hydrogen. And in presence of catalyst, what happens? It goes from alkene to a transformation of making a aldehyde system with a 1 carbon mole. If you see, there are 3 carbons. Since we are involving 1 more carbon, so it becomes 1, 2, 3. This would be like only. I need it 5. Okay. So 1, 2, 3, and 4. So this becomes 1 more carbon chain becomes, but it is going from alkene to aldehyde. So that is what we call as hydroformylation or an also process. Earlier, I was showing the catalyst system that generally is used is this one, having the cobalt center. But now I'm showing with the rhodium one. So we have seen up to this sigma interaction. Now it always occurs like, firstly, the alkene coordination will happen, then alkene insertion will happen. Here now carbonyl coordination is happening. Here it is coordinating with your rhodium. And then the 4th step would be followed by the CO insertion. So these are very important steps. When these two things like carbon monoxide and CH2 are this alkane, they're in cis form, they can easily get transferred or inserted to in between the metal and the alkane. And that is why we see C-double bond O. Earlier it was not there, now it is there. And 5th step is the oxidative addition of your H2. I hope you know about the oxidative addition. Or do I need to explain it?
ये शायद हाँ मैं जानती थी वन में थोड़ा मुझे उतना याद नहीं है पर ज्यादा मुश्किल नहीं है शायद।
तो ऑक्सीडेटिव एडिशन में कुछ नहीं, हमें सिर्फ ये चीज मैं अभी भी पहले ये बता रही थी, मैं आपको थोड़ा सा बता देती हूँ कि व्हाट इज ऑक्सीडेटिव एडिशन। जनरली व्हेन वी take metal here, and metal, if it is in 0 state, that means or it is in +1 state or it is in +2 state, for example, whatever it is. And if it is having the capacity to lose 2 electrons and goes to M+2, it goes to M+3 and it goes to M+4. Okay. So for example, in M0, I will take a condition of palladium 0 to palladium 2. So those 2 electrons, where they go? For example, if I have to activate the H2, so this H2 can get activated, they can take electrons and they can coordinate with your palladium, H and H. So once this kind of symmetry is happening, that is called the oxidative addition. So generally, this lecture is about the hydrogenation of your alkenes. So hydrogenation requires the hydrogen molecule. So इस alkene पे H2 लगाने के लिए H bond को तोड़ना पड़ता है, right? So there are 3 methods. Firstly, the homolytic method. Homolytic method में हम बोलते हैं कि it is going with an equal contribution of the electrons. It becomes a radical. Both the hydrogens are taking 1 electron. That is called the homolytic. Homolytic matlab same. Heterolytic is different, where one will take both the electrons. So this becomes H positive because of इसके पास कोई electron नहीं है, and this becomes H negative. So cation and anion will form. This is what we call as heterolytic. And the third way of having the H2 activation is the oxidative addition, where we don't talk about either the H radical or H positive, H negative. What it does is, if we have a metal center which is having the electrons, be it in palladium 0 or metal in +1 or metal in +2, if it can go to higher oxidation state with a unit difference of 2. So there, if we have a H2, that will bind this H and H, because both of the H has taken the electrons and it has lost 2 electrons, so it becomes palladium 0 to palladium 2. So many coupling reactions, or almost all the coupling reactions, or these kind of hydroformylation or hydrogenation, it involves the oxidative addition. And complementary to oxidative addition, there is one more method called reductive elimination. So this is the reverse of your oxidative addition. Reductive elimination means, as oxidative addition says, we are adding hydrogen and oxidation is happening on the metal center from 0 to +2. Reductive means it will undergo the reduction. That means if it is in +2, it will go to 0 because it will take up. Reduction means gain of electrons. So it will take 2 more electrons and go to palladium 0. And elimination is loss of the product. Earlier, H2 was added. Now it will get eliminated. For example, if I am having palladium in 2, and here it is H, and there is one group called CH2R or anything like that. Because this is also bringing 1 minus, this is also bringing 1 minus. Now, because of the reductive elimination, these two molecules combine together, CH2, CH2R, that is the elimination product, and palladium again will come as 0 state. So this is reductive elimination, which is opposite to that of the oxidative. So there also there is a 2-unit difference of your oxidation state, as you can see. It started with palladium 2, ending up with the palladium 0. Hope this is clear. Oxidative addition and reductive elimination.
इसका कोई और मतलब जैसे H CH2 के साथ जुड़ जाता है, इसका कोई मैकेनिज्म है क्या?
H and H. It is very feasible. If we have two centers, or for reductive elimination, both moieties have to be very cis to each other. So H यहाँ पर है, CH2 यहाँ पर है, they can both coordinate very easily. As soon as ये यहाँ से cleave करेगा, it can take up the hydrogen and it can form a CH3 bond over here. This is the straightforward mechanism, one-step reaction.
Because it is cleave करने,
it is losing the electrons. No, when it will take up the electrons, it will go out, and it will also go out. We don't claim like this as a, how would I say? It is not like charges thing. When both centers are very close in nature, they get combined together and they will leave as it. This is what is happening in this mechanism also, where we came up to this insertion. And now if you will see very closely that we have this hydrogen here and this moiety. This whole moiety, if we will take it as R. So this R and H, they are very close to each other. So they will cleave out as this product, RCH2, CH2, CH2. That H has gone to carbonyl and the whole moiety is as it. So again, it will regenerate your catalytically active species. Okay.
Okay.
So now we are moving towards the rhodium catalyzed hydroformylation. So these are just some points that favored linear aldehyde is due to the step 2, which happens in anti-Markovnikov manner, and the selectivity of linear aldehydes can be increased if. So what they are particularly saying, if we want to have a linear aldehydes and not branch aldehydes, if we'll choose a bulky phospholipids, they would hinder the steric effect, and therefore we will only be having linear aldehydes as a major product. So the next point is recovery of your rhodium catalyst and hydroformylation. So it is very important and economical also. One way of overcoming this is using a water-soluble catalyst, which remains in the aqueous phase and the product goes in the organic phase. So what it is saying, generally what happens in homogeneous catalysis, so I would make a point here. So normally, generally, we have two kinds of catalysis systems. One is homogeneous and other is heterogeneous. So in heterogeneous, product isolation is very, very easy because there are two phases. So one would be gaseous, other would be solid. So you can remove the gaseous product or you can remove your solid product. But in homogeneous itself says that there is no phase difference. Both substrate and the product and whatever the catalyst you are using, it has to be in one phase. That means everything, if it is in liquid, it has to be in liquid, or everything is in solid, it will be in solid. So the product isolation becomes very difficult. For example, here also, if we are having rhodium catalyst, and if it is in liquid or if it is in solid form, suppose, for example, and my alkane, if it is a lower alkane, that would be volatile gas, or it would be in alkene or something, or if it is in liquid. So if both are in liquid, my catalyst as well as my product, so how I will separate and how I will recover my catalyst back? So this can happen if we are using if we use a solvent system in such a way that one is water soluble, one is aqueous medium, another is non-aqueous medium. So there would be possibility that your catalyst is aqueous system, it gets just dissolved in this aqueous system, and your product being an alkene system, it might not be soluble because this is just a CH chain. Hydrocarbons are not water soluble, they are non-polar. So the product that hydrocarbons, they will come in non-aqueous medium. When both aqueous and non-aqueous medium will be together, they will form a layer separation, and you can easily separate it out by distillation or something like that. So that becomes even more feasible. So this is way how we can do with the homogeneous system. Sometimes one more possibility that we can use some solvents which are having a boiling point difference. For example, if I am having a liquid, my product is having a boiling point of 100 degrees. And if my second product, if I have to isolate the two products, and it is having a boiling point of, say, for example, if my solvent is having a boiling point of around 110, so having 100 degrees and 110, I cannot isolate my product. So I need to choose the solvent which is having a higher boiling point. For example, 100 here. If my product boiling point, then solvent I need to choose around 200 degrees. So that distillation say I can separate out my product. So this is why homogeneous becomes a little difficult because the product isolation में थोड़ा issue रहता है. But it can happen if we choose either different phase systems, or if different aqueous or non-aqueous medium, or if we use a different boiling point system. Now, the next thing is the enantiomer selectivity. As we were talking about, enantiomer selectivity is nothing but when we introduce a chiral center. Chiral center is nothing when we have, suppose, a carbon. So all the substituents has to be different. That is what we call as a chiral system. So here, as you can see, if your catalyst system is chiral itself, so one substitution is R, other is CH3, upper main there is CHO, and down one would be H. So all the substituents are different. That is what it is called as chiral. So it can give you this branch form also, this linear form also. This is also one such example where we are using the phosphine and phosphide ligand systems as the rhodium system. So here, if you see, this rhodium is there, and this binap is your chiral ligand structure I've already shown in the earlier slide. So they will give you the enantiomer selectivity. This becomes a branched one, and this becomes a linear one. And the ratio you can see 88:12. And this is the binap system that I was talking about. This is chiral because of those phenyl rings. They are little tilted, so chirality comes into picture. Now, in the chiral system or like this, the phosphine unit is responsible for the chiral induction. If the chirality is in your ligand system, it will transfer it to your whole catalyst, and when the product will be formed, that chirality will also be reflected in your product. So this was it, actually, the last week thing, because the 60th lecture is nothing but the summary of all of this. So we started actually because you joined a bit late. So I will just show you what I started with here. Or we can do one thing. We can just quickly take up the assignment questions, and then if there is any question regarding that, I can get back to these lectures again. So for the last week thing, the week 12, we have these assignment questions, and more or less these kind of questions will come in your exam also. So the first question is, the following compound is better known as. So I think you have missed the first when I was talking about it. So this is the first ever hydrogenation catalyst. That means it is being used for the hydrogenation of alkenes. That means to make from alkenes to alkanes using the H2, and using this rhodium, which is in +1 state, because it is coordinated with your chloride, and phosphines are having lone pairs, so they are not bringing any charge. So this system is actually called as Wilkinson's catalyst because it was given by him. So the question was actually, it is asking whether this is the Zesisol. Zesisol is nothing but your zirconium salt and Wilkinson and Gilman reagent. So these reagents are different. So we are having a Wilkinson catalyst over there. The second question that we have, the hydroformylation reaction is catalyzed by. So as we were talking about, the first hydroformylation reaction that started with, it actually started with this HCOCO4. Don't worry about all these questions because these all have been covered in the lecture series. So the answers are directly coming from their lecture. So if you will just go back and read them properly, you will be able to answer all of them. So this is the catalyst that is actually used for the hydroformylation, or we call it as an oxo process, where if we are using an alkene and using the synthesis gas, which is comprising of C double bond O, this carbon monoxide and H2, it will give you this CHO over there with the 1 carbon more. And this is the catalyst which we use. So as it is involving the cobalt, so the answer is cobalt. Also, we can use a rhodium catalyst, but that was not the option over here. Now, I don't know whether you have attended this one or not. So can you please answer the decreasing order of the reactivity of hydrogenation of alkenes if I use this Wilkinson catalyst? So out of these 4 options, what do you think that would be the best option? That which alkene will undergo the hydrogenation at a faster rate and which will go as the least one? So I will just give you a clue over here. So so take home message is terminal alkenes, they have more reactivity than internal alkenes and less substituted, or we can say less steric hindrance, more reactivity. So now can you please let me know which one is the right option? Just try it, I will help you.
Option B.
Yeah, right. Because that was quite fast, and this is really good if you understand it properly. Because in the option B, if we have here, this is only the terminal alkene we are having. So out of all the 4, this is the only terminal. It has to be greater. In C and D, it already cancels out because it is starting with the internal one. Now, among this and above one, it is having a difference over here. So it is having 4 substitutions of R, whereas only 3 substitutions of R. So this is less sterically hindered. Therefore, it becomes more reactive. So the option B is the right option compared to the other ones. Now we have the 4th question is the substrate that involved in the hydrogenation reaction, which is catalyzed by Wilkinson catalyst. So I already talked about the Wilkinson catalyst, which was nothing but PPH3, whole thrice, rhodium, Cl. And what it does the hydrogenation of alkenes. So what is the substrate that is involved in the hydrogenation? Is it carbon monoxide, or is it CH2N2 or C3H6, which is an alkene, or it's an acetonitrile? Hello?
हाँ, ये CO है शायद, मतलब कार्बोनिल। CO तो एक बार जुड़ा ना। ऑप्शन है।
वो दूसरा कैटलिस्ट है। विल्किंसन कैटलिस्ट क्या काम करता है? इट एक्चुअली डज द हाइड्रोजनेशन ऑफ एल्कीन्स। उसमें कार्बन मोनोऑक्साइड का कोई रोल नहीं है। जो अभी हम रिएक्शन देख रहे थे, दैट वाज दिस वन, which is the hydroformylation reaction, where it goes from alkene to aldehyde. Here in Wilkinson catalyst, it goes from alkenes to alkenes. वहां सिर्फ H2 ही यूज होता है. In presence of H2, it will go. तो अगर आप इनमें से ऑप्शन देखो, only this system which is having ये सारे हाइड्रोजन है, and this is C3H6, which is a propene, and we have, if we are starting with this particular propene and in presence of H2, it will give you this propane. एक हाइड्रोजन यहाँ चला जाएगा, एक यहाँ चला जाएगा, in presence of PPH3. Meeting will end up in 10 minutes. You have to rejoin the link. Rhodium 3 and Ca. Okay.
अच्छा, ये डायजोमीथेन पर को एल्केन बनाने में काम नहीं आएगा ना? मतलब डायजोमीथेन के अनसैचुरेशन खत्म करने में?
This is only applicable for your alkene system. Okay.
Okay.
That is
अच्छा,
why
जो
they said
सिंथेसिस गैस,
this is also a tolerant. If we have any other group besides this alkene, so for example nitro group, which can also undergo the amination, nitro से amine group बन जाए, या हमारे पास अगर CHO group है तो वो alcohol बन जाए, तो that does not happen in presence of Wilkinson catalyst. For that there is different catalyst over there. Noyori catalyst we can use it. Yeah, you were asking something.
हाँ, मैं सिंथेसिस गैस उसमें Fe या निकेल कैटलिस्ट के रूप में काम करता है, मैं उसके बारे में सोच रही थी.
Okay. But actually the question is here talking about the Wilkinson. We need to be very careful. Sometimes complex ka formula is not been given in your question, so you need to know the names of the complexes also. So only just hydrogenation reactions it also be done when we are using a Ren and nickel. Normal nickel ke sath bhi ho jayega, but particularly when we are talking about the Wilkinson catalyst, only what are the substrates that it can do? It can produce and hydrogenate only alkenes. Okay. So therefore, जब आंसर करो तो देन यू नीड टू बी वेरी पर्टिकुलर एंड केयरफुल जब क्वेश्चन में आपको क्या पूछा गया. इज इट क्लियर नाउ?
हाँ हाँ, मैं जब ग्रेजुएशन में पढ़ती थी तब भी भूल जाती थी. मतलब ये सारे नाम थोड़े इधर उधर हो जाता है. विलियमसन है, विल्किंसन है, बहुत सारे हैं.
But even if अगर you will see around this, so इस पूरे lectures में if you will see very carefully, there is no talk about CH2N2 या CH3CN या carbon monoxide. I'm talking about just this particular course. तो नहीं भी पता होगा उसके नाम के बारे में, देख के ही समझ में आ जाएगा कि what is going to get reduced. I understood your part that carbon monoxide with H2 it also gives that carbon dioxide in this one, but that we don't call it as generally there. Wilkinson catalyst will not be having any role. So you have to be careful for that. Okay. Now we will take up the fifth question. The rate determining step of the olefin hydrogenation reaction catalyzed by this. Now, what is this catalyst?
This is Wilkinson catalyst.
कैटलिस्ट के ऊपर 4-5 क्वेश्चंस एक साथ आ जाएंगे because it involves a lot of things like mechanism part, the different steps of your mechanism, what substrate you are using, what product you can get. So बहुत सारी चीजें आ जाएंगे. So this is your Wilkinson catalyst, and now it is asking like which one is the rate determining step. कौन सा स्टेप जो है वो rate determining step होता है in case of the Wilkinson catalyst. So what is rate determining step, for example? Do you have any idea about it? Like इसका मतलब क्या होता है?
जो स्लो स्टेप होता है वो ही रेट डिटरमिनिंग स्टेप होता है.
तो वहाँ हम इसका रेट को जो है देख सकते हैं कि
आपकी आवाज थोड़ी कम आ रही है.
हेलो, अभी आ रही है आवाज?
हाँ.
So I was saying that you were right in saying that rate determining step is the slowest step, and there only we can determine the rate of the reaction, like with what rate it is actually moving and doing the things. Now it has given 4 options, and these 4 options are a part of the mechanism only. जो हम catalytic mechanism देखते हैं, this is the part of that mechanism only, which involves the oxidative addition step also, reductive elimination also, cis trans rearrangement, and olefination, that olefin insertion step. So out of the 4 steps, which one is the rate determining step? So actually this is not something related to your mechanism or something. This is a bit more study or theoretical thing. From studies, we get to know which among of the four are the rate determining step. So, do you have an idea, or I just let you know the answer? Because this is already
I
covered.
think the option will be A.
So, oxidative addition is very fast step over here, because that becomes the first step. So the first step has to be fast to get your reaction very easily. It can't be like a slow step, right? If first step में ही अगर वो उसको देरी लग रही है, so how it will further move? So here in this particular case, olefin insertion is the right option. It is the slowest step. So if I just show you that if we are having this P3RHCl, right? So there P, I am talking about the PPH3. This is in rhodium in +1. My voice is audible to you?
Yes.
So first step is the loss of one molecule of, it becomes RHCl. Then it will go and H2 oxidative addition will happen. So in oxidative addition, because it is +1, ultimately it goes to +3 and one H here, and Cl here. Then the followed step would be having an alkene coordination. Firstly, the coordination will happen. So if I am taking this particular alkene, this ethylene, so it will get coordinating with your alkene, which you can make as a dash bond. H is here, Cl is here, and H is here. So when this H and this particular thing are cis to each other, now the olefin insertion will happen. That means it is going to make a sigma bond or the direct bond between with the metal system. So this H will go here and CH2 will bind here. So this become a rate determining step. This is bit slow step. Does not happen at a very faster rate. So ultimately it will form like CH2, CH3. Now we have H and Cl and this P. This CH2, CH3 and H are trans to each other. Then trans isomerization will happen and it will form, both will come as a cis because for reductive elimination, both of them has to be cis to each other. And with the reductive elimination, both will come as an alkane and you will get your catalytic active species back. So the take-home message was just that here the olefin insertion is the rate determining step because it becomes a slow step. It's not very, very fast to have the insertion with the rhodine. Okay, so the right option is olefin insertion. But if I would say that if I'm taking a different catalyst, for example, in case of, I think, oxo process, the hydroformylation process, there also we are using alkene, but in presence of CO and H2. So there H2 oxidative addition happens at the sixth step. That happens at sixth step. That is not the first step. And there this becomes the rate determining step. So rate determining step would be different for different mechanism, depending upon the studies, like which is becoming the most slow step. And we cannot just determine looking at the mechanism, okay, why it is the slow step and why it is the fast step. It depends upon the kinetics. And this we have to get to know from the different studies, like why the rate is coming like that way. So it is also like not like the thumb rule. Like if in one particular mechanism, olefin insertion is the rate determining step, then that has to be rate determining step in all the other steps. No, with the different catalysts, with the different processes, it will be following different kinetics. So you need to keep that thing also in mind. Okay. Is it clear?
Uh-huh.
Now, can you please tell me the answer for this question? The number of chiral center, I just told you what are the chiral center. I hope you already know. The number of chiral center present in the following diphosphine ligand is. So this is your ligand. Now you need to find out how many chiral centers are there. Just give it a try.
I think the D option of 4. Um,
So can you please help me in which are, is this a chiral center?
um, कौन सा?
Here, which I have marked as circle.
हाँ ये तो है।
This one?
हाँ।
Okay, so 1 2
हाँ।
is second. What about this one?
नहीं, इसमें
Okay,
तो एक एल्कीन।
right. So this इसमें तो आएगा नहीं. What about this one?